Hello again and welcome back to my computer vision channel. Today we will be talking about Trackformer, a first transformer model for multiple object tracking. So here's the plan for today. So we'll start with a brief overview of what tracking is, how is it different from object detection, why you might even want that, and so on. We'll look at the foundational model for Trackformer called Detr. And then we'll go through the different aspects of Trackformer itself, the method, how we connect query inputs for the decoder from one frame to another, how we calculate loss, how we can pre-train on the tracking data, that is when you actually have a video with annotated track IDs, or how we can pre-train on detection data. When you don't have videos, you just have object detection data set like Coco, but you still want to use that to do some tracking, and that is actually possible with image augmentation techniques. Then we'll talk a little bit about how the actual tracking is done with Trackformer, and then we'll discuss the results. Okay, so let's start with the task itself. Multiple object tracking, how is it different to object detection and why we even need that? So this is the official website for multiple object tracking challenge, one of the primary challenges used in papers, in leaderboards, and so on. So this is an example of how a task looks like. So this is basically a video of, I guess, bus, a double-decker from London. And so if we activate public detections, so this is the object detection part, we can see that we basically look at people and how they move. And the main difference of tracking to just object detection is that we need some persistence of instances that we track. So instead of just saying that here, let's suppose here that this is a man, for example, this is a person, and so on. We want to track them frame to frame. That is to allocate some track IDs to every specific person in this case, and make sure that we persist the same track ID throughout the entire video, ideally up until the end, instead of just losing and then thinking that it's a different person. So this is the main goal of multiple object tracking. And the actual metrics in multiple object tracking sort of focus on detection and tracking at once. So detection is actually plotting the bounding boxes and predicting the class of the object if we are dealing with detection tasks with multiple classes, but also tracking the same objects frame to frame and making sure that the same instance is stable and it gets the same track ID frame to frame. So why might we need object tracking as opposed to just object detection, for example? So one of the most common cases is just counting. If we come back to the video and let's say you want to solve some traffic problem, or you want to understand how many people are there on the street in any given time, you'd notice that by just looking at the static image, it's quite hard to tell because when you move on to different frame and like you detect a person standing there, right? So you don't really know if this is a new person and you need to increment your counter, or is this the same person that you have seen in the previous frame, and so on. So to actually count objects as they appear and disappear, which is useful for traffic, for marketing, for city planning and stuff like that, you need to track objects and not just detect them. Object tracking also allows you to do some primitive action recognition, because now you, instead of just seeing a frame, a fixed image, and detecting an object, you also have actual video, and you know that this is the same object sort of moving about in space. And so that allows you to do some primitive action recognition. So for example, for traffic control, so let's say here, U-turn might be forgiven, so you forbid cars to do the U-turn here. But then if you just look at the car that is maybe doing something, and if you just look at the image, again, it's really hard to tell what the car is doing. Is it just standing there? Is it, performing just a normal left turn or right turn? Or is it actually doing a U-turn? So again, if you just have tracking, you can already say that this is the trajectory of the object, and this is what the car is performing. And from there, you can track what exactly it is doing. But it's still not the same as maybe specialized neural networks that try to predict action itself, and that might be more complex and more accurate. Here instead we just get the actual coordinates of the object as they evolve in time, but still that gives much more information than just static object detection information. And finally, in robotics, so I've just recently bumped into an example of how you can use that for picking up trash. So again, with object detection, that would be possible. So you'd imagine a robot. Here's a video from one of the robot manufacturing companies. And so, yeah, you can basically make it pick up trash. Let's scroll. Yeah, so here's the thing about picking up trash. Again, you can do that with object detection, but then your robot will be sort of short-sighted, myopic. So you'd basically have to write an algorithm that says, let's pick up the thing that is closest to us, for example, right? But then it's easy to imagine that, if you have a lot of trash to pick up and you always move to the closest, then you might miss something that, you basically went out of your view, and then you basically forget about it and you don't pick up everything. With object tracking, you can actually track those things. So you can say that, okay, I've seen this object. I've remembered that this is the object that I need to pick up, and basically make sure that I collect everything before moving on to next objects, instead of just losing that and forgetting about it. So that object tracking basically introduces this concept of memory and, being able to track something from frame to frame. So before transformers, the most common approach to tracking was tracking by detection. And that basically means that, if you have 2 consecutive frames of the video, you first detect objects in both of these. And detections are basically, they're not actually saying that, this is person 1, person 2, person 3. Instead, they're just saying that, this is a person and this is a person. So then you'd need to somehow connect the detections, the bounding boxes, from one frame to another. And that was typically done with algorithms that basically just use the frame coordinates. And you can imagine that it actually works quite well, because usually, if we are tracking people, they don't usually move that fast. And so if you have a really high frame rate, you can sort of know that, the frame does not move that much. And so you can confidently say that, if this was the person and moved slightly over here, that's probably the same person, and so on. But then again, sometimes you will be wrong. So for example, if one object is moving like this, and then another object is moving like this, and here they sort of intersect. And so from there, it's really hard to tell if this is the object that was moving like this, or it was moving straight. So it's easy to get lost, especially if you have now a lower frame rate, if the camera moves, if you have occlusions or partial occlusions, so it becomes harder and harder. So there was another approach that was more nuanced, called tracking by regression. It did use more information. It actually tried to basically look at the image, compute some features for the image, and try to predict offsets of that frame in the next picture. But you'd still rely on this heuristic components basically to connect the prediction from the 2 frames. And so what Trackformer does is it basically predicts everything end to end. So you would feed in the previous image to the Trackformer and then ask it to find the same objects, or maybe initialize a new track, a new object in the new picture. So this basically removes a lot of heuristics that might work in some cases, but then not in others. And so replacing that with the actual model that is trained end to end is supposed to give you that boost in accuracy, because now if you have a more complicated model, more data, the model might learn more nuanced behavior. So in the examples of, intersecting tracks, it will actually look at what the objects look like and be able to make a proper prediction. And so here is the papers with code leaderboard for multiple object tracking. So you can see how that was developing in recent years. And so Trackformer is over here. So it was a slight improvement over the previous one, but still it's a good model to start with. It's relatively simple, but then it's not the last. So we have a lot of new stuff coming out. Hopefully I will talk about that in my next videos. Next, let's talk about Detr, the foundation model in Transformer itself. So this is the diagram for the Detr. Actually, I have a more in-depth video about Detr, so you can check it out. I will leave the link in the description. But now let's just quickly go over that so that we can understand what will happen next. So Detr is the model for object detection with transformers. So by object detection, we mean that given an image, we basically draw these neat bounding boxes around objects and also predict classes. So Detr was trained on the dataset that was called Coco, which has 80 classes such as bird, dog, person, car, pizza, train. 80 is not that much, so there's a limited set of categories, just the most popular ones. So the way it works is we start with the image that basically gets fed in from the left. We start with image backbone. That can be a convolutional-based model like ResNet. It can be a transformer-based model like Swing Transformer. Doesn't really matter that much. And the result of that is basically a downsized version, so really low resolution version of the image, like 20 by 20, but with every pixel now holding an embedding with features important for the actual image recognition. So then we pass that to the transformer. So transformers always deal with sequences. So before starting our transformer encoder, we need to flatten everything out, basically laying out all the pixels in this neat row. And because of that, we sort of lose the positional information. And as usual in transformers, that is solved by adding this positional encoding, which is just an extra embedding that encodes the position that was originally there in the pixel into the vector itself. Then we have the encoder. So encoder self-attention is basically just transforming that sequence, arriving at sequence of the same length, same shape, but now more refined, basically allowing different pixels to pay attention to each other, to create more refined representation of features sort of after this self-attention, after taking a closer look at the image. Then we have the decoder. So decoder is the primary part we will be interested in. So decoder basically maps this sequence that had the same shape as the original image or downsized version of the image after backbone. It maps it into the actual object predictions. And to do that, we start with some object queries, for example, 100 of them. And in case of Detr, they're just statically initialized, meaning that they're basically initialized as 100 static trainable vectors. Trainable means that we actually train them, arriving at good initial starting point for queries. Static means that they don't depend on the actual picture. So they will be equal no matter what picture you feed into the model. And so the output of them, of this decoder, is again a sequence of the same shape. So 100 vectors, each vector now trying to detect some object. And so then we project that down using feed-forward networks. So we project every query output into class predictions and bounding box predictions. And so bounding box predictions are basically 4 numbers for the size, the width, the height, and the coordinates of the bounding box. And the class predictions are basically class probabilities for one of the 80 classes in Coco dataset or the special no object class. So ideally, we want the model for this picture to predict 2 birds with perfectly matching bounding boxes. But then again, like when we just start to train the model, obviously it will be initialized with just random weights. So it will not actually be able to detect anything. And so in order to train it, we need some mechanism to match random bad predictions, random bad detections to ground truth objects, such that it will be actually useful, so that we can train the model using backprop, basically meaning that we need to give incremental feedback to the model on how to become better. And that is the primary novelty of the Detr, and it is solved here using the so-called Hungarian matching loss. So once again, let's say that the model is just initialized, it's outputting a lot of random predictions sort of all over the place. And so we have to solve this matching problem. So like what if the bounding box is somewhere here in the middle? Like, do we match it to the left board, to the right board, or none of these? So basically, how do we do that? How do we do that in such a way as to be able to give this incremental useful feedback to the model so that it can actually train to detect everything properly? So as I said before, it's solved with the Hungarian matching loss. So let's say that the object predicts 2 birds, and then all the other queries are just saying no object. And the prediction of the model, of the Detr model, is basically a set. So it does not really have order to it. And so we want to match it to the ground truth objects somehow, so to the first bird and to the second bird. And the way we do that is by basically iterating over all possible matching combinations, and we choose the one that minimizes the loss. So let's say if one bounding box was this one and one bounding box was this one, we iterate over all possible matching, and then we find that connecting this bounding box to this bird and this bounding box to this bird gives the smallest loss, and so this is the matching that we go for. So the actual algorithm comes from the special sort of graphs called bipartite graphs. We'll not talk about it here, but basically it's more effective than actually trying out all the possible combinations. It's basically able to solve the problem really quickly, so it's a really effective algorithm. And here's a different example of where the predictions are maybe not as great. So here we did predict 2 birds, but then we also predict a third bird that is not on the image. So maybe it was just the duplicate bounding box prediction for the same bird. And then we also predicted phantom cat, let's say somewhere here. And so after this Hungarian matching loss, we'll see that the birds got matched with something, right? And then this third bird will have to be matched with something as well. And since we only have 2 birds on the picture, it will have to be matched to no object class, and so is this cat. And so basically by doing the classification loss on top of this, you would penalize the model for duplicates, for predicting a third bird that is not really on the picture. You would penalize the model for predicting phantom objects on the background. So again, this is really good. And let's just go over what input to the model is and what the output is. So the input is just an image, just pixels, 3 color channels, red, green, blue. And for training, we also have labels. In this case, object annotations, the bounding box, the 4 coordinates for position and size of the bounding box, and the class. So the class is basically an index from one of the COCO datasets, 80 classes. And we might have a variable number of objects on every image. We might have 1 object, 3 objects, 15 objects. You never know ahead of time. So the output is a fixed set of predictions. In case of Detr, always 100. So every prediction predicts class probability. So it will have 81 numbers, 1 number corresponding to the probability of the no object class, and then 80 numbers for the probability for every class, and then predicted bounding box, the actual 4 coordinates. So it's rather interesting for our object tracking problem that prediction is a probability for a fixed set of classes. So if you look at like tracking problem, right? When a person looks at this image, we can see that the person will think about something like, okay, here's the woman crossing the street, here are 2 people walking down the road, and here's the person in black. So we actually add more details to the objects that we detect. Unfortunately, that's not how object detection does it. So object detection will just say that this is a person, this is a person, this is a person, this is a person. So it basically erases those details that could have allowed it to do the object tracking, or at least matching objects from frame to frame. And this is all because object detection really solves a simpler problem of just detecting the person and not paying attention to the actual details. And let's also talk about the actual loss for Detr. So the loss should train the model. It should penalize the model for outputting wrong predictions. And we want the model to predict correct bounding boxes, the actual locations of objects and their size, as well as the class. And so for bounding box predictions, we might use mean square error. Mean square error basically means that we have these 4 numbers for the bounding box, and let's say the predicted bounding box is slightly different to the ground truth, and so we'll basically compute the difference in the coordinates. In case of Detr, I think it's for upper left corner of the bounding box, and then the size, so the actual size difference between the width and the height of the bounding box. The problem is that approach, so it works. The problem with it is that it basically allocates higher loss to bigger objects. So if the object is really small and then the predicted object is really small as well, even though like this difference is really, really huge, right? So we don't even intersect with the object. The actual mean squared error is quite small as well because just all the sizes are small. That's the problem. And so to deal with that, there's also a different loss called IOU, which basically says that if we predicted this bounding box, we look at intersection and we divide that by the union. And so this gives us the metric that will be always 1 if you have the perfect match, and then it will be 0 if the bounding boxes do not even intersect. And this loss is more reliable for small objects. So for small objects, it will work exactly the same way. Even though the objects are small, the ratios will stay the same, so it will work better for small objects. And then for classification, we use the typical cross-entropy loss between predicted class and the ground truth class, as well as for the special no object class. Now let's talk about the actual Trackformer. So just a reminder of how Detr looked like. So we'll take the same exact model as a base, and we'll see how we can use these queries to make it track objects frame to frame. So this is the scheme of how Trackformer works. So basically now we look at different frames in time, and we try to use predictions from the previous frame to track objects in the next frame. So for example, we start with this picture, we feed that into Detr model. So this part is exactly the same as we've seen in the previous slide. So backbone, encoder, decoder with, in this case, queries being statically initialized because this is the first frame. And so we get some predictions. So this guy predicted no object, all the other guys predicted the person somewhere. And so we take these queries as an output, and each query here, each square is an embedding vector, the output of the transformer decoder, and we use them to initialize the queries on the next frame. So you can see on the next frame here, or rather here, we can see that every person moved slightly. So this woman moved to the right, this couple moved a little bit down the road, and then we have a new person appearing from the left here. And so we have 3 objects, 3 queries that sort of carry over from the previous frame. We use that as 3 queries for decoder input. And then the rest, 97 queries, again, will be statically initialized. And then we asked Trackformer to basically find the positions of the first 3 queries in the new picture. And then someone else also detected this new object. And so when we detect a new object that was not present in the previous frame, we basically initialize it with a new track ID. So the difference with previous tracking methods here is that Trackformer is trained end-to-end, and it is free to put whatever information it needs into the query itself. So it's not just the bounding box, it's not just the class, it's not just the coordinates, it's the whole embedding vector. And so Trackformer or Detr component of it might encode all sort of useful stuff in there. For example, saying that, this is a woman moving to the right with black shirt, and this is a man in black, and so on and so forth. So now the model is free to express itself however it wants in the means of useful information it puts into these embeddings that get carried out from frame to frame, thus basically allowing it to properly look at the previous object in the next frame and detect the previous objects in the next frame. So there will be a couple of special cases of how that happens. So one special case is when the object was not present in the previous case, in the previous frame, and we detected it. So this is a new object arriving at the scene. Another special case is when the object was present in the previous frame, but then it got occluded. We no longer see it, and so it is now connected to no object class. So let's go over all of that one more time. So at frame 0, at the very beginning, we initialize 100 object queries statically, as in Detr, so they will be comprised of trainable parameters independent on specific picture. And then we detect 3 objects. So 3 of the query outputs will get matched to some objects, and we initialize those with the new track ID. Then when doing the detection for the next frame, frame 1, we carry over those 3 objects from the previous frame and initialize other 97 from scratch. And so the 3 initial, in this case, 3 initial objects already were there, so they basically got predicted once again. And then the 4th object was predicted by this statically initialized query. And so 4 object queries now carry over to the next frame. And in this case, 1 ground truth object disappears, so only 3 objects remain, and that object that disappeared, the query corresponding to it will have to be connected to the noObject class. Let's also look at model inputs and outputs. So during training, the input is actually just 2 images, so frame 0 and frame 1, the previous frame and the next frame. So we are not really feeding in the actual video stream. We are just feeding in 2 images. And this is a little bit reminiscent of, let's say, reinforcement learning, because deep learning algorithms want data to be random, in a sense, at least random and independent of each other. So it's not good to train on the actual sequence of video frames, because then you basically lose the convergence guarantees of your backprop of gradient descent. And so what we do instead is we sample random frames from the video and basically take frames from different videos, combine them into batches, and then train on that, basically randomizing the sort of input that the model gets. Again, each frame has some object annotations, each annotation being bounding box coordinates, class, and this time actual track ID. So the actual ID of the instance of the object. And the output of the model is, again, fixed set of predictions, let's say 100 of them. Each prediction has class probability, bounding box prediction, and it's really an interesting detail here because Detr itself does not predict track ID, and nor do we want it to. Instead, this track ID is implicit in the position of the query that predicted that object. So it's not really explicitly predicted, it's just there from which query predicted that object. Now let's talk about the loss. So what sort of loss can be used for tracking? And so in case of Detr as well as Trackformer, we can basically divide the loss into 2 components. The first is matching. So how do we match the output of the model to ground truth objects? And the second is the actual loss. And so in case of matching, Detr was quite simple. You always just take all the model outputs, pass them through the Hungarian matching loss, and there you have your matching. In case of Trackformer, it's a bit more nuanced. And it basically repeats what we already said about the model itself. So some queries get carried over from the previous object, and such queries, like these 3 guys here, they do not participate in the Hungarian matching loss. So instead, for them, we just have direct match that this query has to correspond to this specific object, and this query to this specific object, and so on. We only use Hungarian matching loss to new static queries. So basically, for these white guys here that were not previously matched with anything on previous frames, we get some model predictions. Some of them will predict some objects, some of them will output an object class, and then we use Hungarian matching loss to find to which ground truth object this query is matched in the best way. And then similar to the objects that were there on the previous frame but then disappeared, like this blue guy here, so it is no longer an object in the new frame, and so we take this query corresponding to that object and then connect that to an object class. And so this is how it will look like. So the model predicts something like that. And so the first 3 predictions here that were initialized by the queries that got carried over from the previous frame, They are not participating in the matching loss and just instead directly connected to the ground truth objects. And then for new objects here, we can imagine that, for example, with predicted person, cat, another person, and two object classes. Then for this part of the model, we run this Hungarian matching loss, let it iterate over all possible combinations, let it find the best match for us, which in this case was this person prediction, so it got matched to the fourth object, and then everything else gets matched to no object. It's useful to think of that as basically adding order to our set prediction. So Detr itself is often referred to as direct set prediction. So this Hungarian matching loss part, it basically ignores the order of predictions. Thanks to the fact that you feed that into this matcher that tries to iterate over all possible permutations, it ignores the order, which is contrary to our tracking job. So for tracking, we need to preserve the order of the objects in order to keep track of their track ID. So we introduce this order for objects that are persistent from frame to frame by just taking them out of this Hungarian matching loss and instead having this direct match component. And then after we've done the matching, so after we have this connection that this object query is connected to this ground truth object, we basically apply all the same losses that we had in Detr. So we look at bounding boxes, MSE, IOU, intersection over union. We look at classification, cross-entropy loss for the class prediction, and that's it. So notice how there is no explicit component in the loss for track ID. So the loss that we compute here is exactly the same as in Detr, but you get that tracking properties by matching. So thanks to the fact that, this object query here got matched to this person, even if prediction is way off, since it does not participate in the Hungarian matching loss, the loss will basically drive this bounding box into the correct position always, instead of trying to match it with a different object, for example. So thanks to the fact that we've already directly connected them during tracking stage, we already solve for this track ID persistence, and we can just use the normal Detr loss to train the model. Now let's discuss how to train having actual tracking data. So first you need to sample those frames. So basically you want to go from a sequence of frames that are all dependent on each other in some way. You want to go to independent pairs. So one frame in the pair follows the other, but then the frames themselves are independent of each other. And so you would get a lot of videos, sample random frames from there, and thus have your IID random sampling that works quite well with gradient descent. So this technique of, and we sample not just two consecutive frames, but instead we take a frame and then take another frame that is k steps behind that one. And so this k is basically a parameter, and what it allows us to do is to have what is called temporal augmentation, where we, instead of always looking at consecutive frames, we might skip some of them, thus basically making the work harder for the model in case our training data is really high quality, high frame rate, and then in reality you would use the same model with lower frame rate cameras, for example. So you want to simulate that. So by skipping more frames, you basically make the job harder for the model. Also, we've talked about how we do loss and how we do matching in Hungarian matching loss in the direct match. And so majority of training for tracking basically happens in two cases. So one case is when a new object appears, and another case is when an old object disappears. And so that actually happens quite rarely in videos, because mostly frame by frame, you just have the same object slightly moving within the picture. And so we want to augment the training data set to have more interesting examples. You'd have false negatives where you had some object present in previous frame and in the current frame, but you sort of remove the detection, the query that was supposed to carry over, and instead let the model detect it from scratch, thus simulating the situation where the new object just appeared. The old picture, the previous frame, does not really participate in the loss, so it's safe to do. You're just saying that you had these queries and this one is missing, so you have to detect it, initializing new track ID. We also have false positives, where we randomly carry over a query that was supposed to predict random background object, and we put it as an input to our Trackformer on the current frame, thus letting it look at this input query and then seeing that it doesn't actually correspond to objects that are currently in the picture, and basically learning to remove it. Let's also talk about other types of data that you can pre-train on. So thanks to the fact that we are only looking at pairs of frames, we can actually bootstrap our way into tracking by just using detection data. And so the main reason to do that is that it's much easier to come by detection data. So there are more data sets. And if you're solving a novel task, for example, picking up trash on the street, and there's no specific data set annotating tracking for trash, it's much easier to find data sets for your specific classes that you want to predict if it's just about detection. It's also easier to annotate, because for detection data, you just need to draw the bounding box and assign a class that you're interested in. For tracking, you'd have to do that for every frame within the video. So that's like 24 frames per second more work for every second of the video, and the video might be quite long. So it's just a lot more work to get the data annotated. So how we do that is we take an image from the dataset, from the detection dataset, so we'll know which objects are there and the bounding boxes for them. And then we perform some image augmentations like random resize crop, and basically create this different version of the image. And we consider this different version of the image to be like the previous frame. So it will be slightly different, and so you'd still get some useful signal, and you would train the model to look at the image, look at slightly different image as if it was the next frame, and learn to connect the objects and track the objects from the previous frame to the next one. So this is the Jupyter notebook that I will be showing in the next video when we will be reading Trackformer source code. But here's the actual data set called CrowdHuman. So CrowdHuman is object detection dataset focused around people. So most of the images here are images of people. And so here we can see an image from the dataset, and then a slightly differently augmented version of the same image. So if you scroll up and down, you see that, we have this man, and it sort of looks like he's moving to the right. And in the next picture, he almost completely disappeared. And so you'd have slight differences like that in an image. So the image itself, there's just one image in the dataset. So that's not really a video. But thanks to this augmentation technique, so random resize crop basically crops out a random portion of the image and then might also resize it a little bit. So that thanks to these random augmentations, we actually get that effect as if it was a slightly different frame of the video. So obviously this is not ideal because this is a good picture actually, but a lot of these pictures, let me find something. So this is another example. So in a lot of these images, the people are not really moving. And so it's a bit less quality data, I guess, because the model trains on static images where in a lot of cases, people just stand and pose for the picture. And then obviously in the real tracking scenario, they'll be moving. So the actual look of how objects look like will be different. But still, it's good for pre-training. So pre-training is usually about having a lot of maybe lower quality data, thus allowing you to initialize the model, learn at what the world is and what objects you have there, and then you ideally have a higher quality data set for fine-tuning to actually make sure the task that you're trying to solve is solved really well. Finally, let's talk about the actual tracking. So how do you use the trained model to do object tracking? There are quite a few tricks there. So first of all, now we have all the video frames in order. So we start with the frame 0, initialize all the tracks, and then start feeding frames one by one without skipping, without randomizing. And every time a new object appears, we don't know when a new object appears, but instead we'll let the model figure it out on its own. So if the model thinks that a new object has appeared, we'll see a new query output basically indicating that. And so in case we have these newly initialized detections, we basically assign new track IDs to that. For detections that carry over, so from frame to frame, we use existing track IDs. Another trick here is to keep the query alive if the object has just disappeared for several time steps. So this is basically to help with the situation where you have temporal occlusions. So for example, you'd have a person that briefly walked behind some truck or something like that and then reappears shortly thereafter. So it will be ideal to still keep track of that person, and this, like, a human can deal with the task quite easily. And to do that, we basically have this heuristic parameter that says for how many time steps we want to keep this query, and we just do not throw it away, and we keep it there. Let the model look for this object in the next frame, and the frame after that, and the frame after that, for example, and then if the model manages to find that object a few frames later, then we basically use existing track ID for that one. So we basically didn't lose this object despite it being absent from the frames for a few seconds. And then if we couldn't find the object for too long, we throw it away. So again, this helps with temporal occlusions. This is not used in training, so this is just one heuristic parameter that lets the model behave a little bit better in this case, but it's nowhere, there's nothing special about the model or the way we train it to keep this behavior. Now let's talk about results. So if you look at the paper itself, they quote results for multiple object tracking, mostly on this multiple object tracking 2017 challenge. So this mod challenge basically have two parts, public and private. So public part is aimed more at like old school object tracking algorithms that rely on already existing bounding boxes. So basically they have public detections from stuff like YOLO or regional proposal network, and then let algorithms compete in how to match these existing bounding boxes from frame to frame. So this is not really applicable to Trackformer, although they do report some results for a slightly different version of how to do that matching, which is not really working out of the box for Trackformer. So it's not really that interesting to look at that. Instead, we can look at private detections. So private detections is your end-to-end detections where you just have a raw video and you let the model track everything on its own. And you can see here that there are basically two sets of models. And in this set, Trackformer seems to be much better than everything else. And then some models in this set are really much better still. So this basically, what this demonstrates, so these models are all trained on the same data as Trackformer, and that is the crowd-human data set, which just contains images and object detection, so no actual tracking, and then the mod training data itself. These models are all trained using much more data, different tracking data sets, different object detection data sets, so it's not really fair to compare them. And so when trained on the same data, we can see just how much of a performance gain Trackformer gives, even though it's really a simple model. So Detr is by far much simpler than everything that came before that, the old school object detection models like regional proposals and YOLO, and everything that came after. So all those over complications of deformable Detr, depth Detr, Dino, and so on. So Detr is really simple, and so is Trackformer. So it's really cool to see this improve in quality from this really simple model. I guess that demonstrates the usefulness of the concepts and the power of Transformer itself. But even at the time, it wasn't really the state of the art, strictly speaking. Although maybe you could get there if you scale it up, if you train more data. I'm not sure why it wasn't done in this paper. So this is really it regarding Trackformer. I also want to take a moment to advertise what else I have on my channel. So today we were talking about Trackformer algorithm. The very next video I want to make about reading the Trackformer source code. So if you still have questions about some particular details about how the model works, hopefully that video will help answer a lot of questions, because there's always a lot of details in the code that you just miss reading the paper or watching videos like this one. I also have a lot of videos about modern object detection. So stuff like YOLO, which is old school CNN-based model, which is still quite popular, and because it's quite accurate and fast. I also have a lot of videos about this transformer-based series of models. So Detr, deformable Detr, DAP Detr. So Detr was quite useful today. Deformable Detr will be useful in the next video when we'll be reading Trackformer source code. So check it out. Then DAP Detr, denoising Detr, Dino. All of these basically build up, slightly making models more complicated, but improving the quality as well. And the Dino was state-of-the-art for quite some time, and it was the first transformer model for object detection that achieved this status. I have a couple of videos about text models like GPT-1 to BERT, and then a really cool model called Grounding Dino that allows you to do what is called open set object detection, where you basically provide a model with a prompt and let it detect objects using the prompt, which allows you to do the object detection in novel categories or even more complex stuff like detecting objects by reference expressions, something like third sheep to the left, for example, and so on. So it's also really cool. I want to make another video that is not out yet about Detr, current state-of-the-art object detection detector. So we definitely have a lot to cover, so hope to see you soon.